In this video, we will find and classify any critical points of f of x equals x to the 2/3 and g of x equals 1 over x. First, we'll begin by reviewing the definition of a critical point. X equal to c is a critical point of the function f of x if two conditions are met. First, if x equals c is in the domain of the original function f of x, and then either the derivative at c equals 0 or the derivative at c does not exist. Let's look at our two examples. Here we have the graphs of x to the 2/3 and its derivative 2/3 x to the negative 1/3. As we look at the graph of f of x equals x to the 2/3, we see that this function is defined everywhere. So we would say its domain is negative infinity to infinity. And while it's defined everywhere, we do notice that near 0 we have this cusp-like behavior. And if we recall, the derivative of a function does not exist at the point of the cusp. So we see at 0, just if we were looking at this graph, we would know the derivative does not exist there. And we see that here in the graph of the derivative. Notice at 0, the derivative function is undefined. So we would say its domain is from negative infinity to 0, not including 0, union 0 to infinity. Now, if we want to take the derivative and identify if there's any critical points, we would start with the original function, its derivative 2/3 x which could be rewritten as 2 divided by 3 times the cube root of x. First, if we're looking for critical points, we might consider when this function equals 0, but it's the case that this would never equal to 0. We know when it comes to a fraction, only the numerator really affects the whole fraction going to 0, so since 2 is never 0, we would say that the derivative never equals 0. Next, we would want to consider when does this not exist. So we would see that the derivative does not exist, specifically when the denominator goes to 0, which is when this term would go to 0. It would take the entire denominator with it to 0. So at x equals 0. So we would have that this does not exist at x equals 0. Okay. So since the derivative at 0 does not exist and at x equals 0, we know that's a point in the domain of the original function. Based on these two criteria, we know x equals 0 is a critical point of f of x. We were also asked to classify this critical point, so now we'll use the first derivative test. So we label our critical point, we pick test points to the left and right, the two intervals, and we evaluate these in the derivative. So we would find f of -1, or the derivative at -1 is equal to this, which would give us a negative value. So we see the derivative is negative at -1, and this corresponds to the idea that at -1, we do see the slope of the tangent line of the original graph is negative. Okay. Evaluating 1 into the derivative, we would get a positive value, which at 1, definitely we see the slope of the tangent line to the original function has positive slope. So we would get the conclusion that the function is decreasing before 0 and increasing after 0, which definitely does correspond with what we saw of the graph of f of x. So based on this, we could say that at x equals 0, the function f of x has a local minimum, and in this case, as we can see, this local minimum is actually also an absolute minimum. Okay. Here we have the graphs of g of x equals 1 over x and its derivative. From this graph, we see that g of x domain is all values except x equals 0, and that makes sense because the function, we know that 1 over x does not exist when the denominator is 0. And similarly, for the derivative function, -1 over x squared, it also exists at all points except when x equals 0. So its domain is also negative infinity. Finding the derivative, when we're looking for critical points, we'd want to say, does the derivative ever equal to 0? And just setting up that equation, we see that this will not happen. Okay. This will never happen because for a fraction to equal 0, that has to do with the numerator, which -1 will never equal 0. Okay. Next, thinking about when does this expression not exist, and we do see that this expression would not exist at x equals 0. So we did find that while the derivative at 0 does not exist, we recall that x equals 0 is not in the domain of the original function g of x, so our conclusion would be that x equals 0 is not a critical point of g of x. And indeed, there's no other candidates for critical points, so for this function, there are no critical points.